All right. So this talk is about gluing. Specifically, there were two equivalences discussed in the two talks earlier today. Something for Whittaker, so to say for the non-degenerate part of the Whittaker category and for the degenerate part of the Whittaker category. And in my talk, I want to explain how this, well, did I say I mean, depending on which version you take, it's an equivalence or a fully faithful embedding, but anyway. In my talk, I'm going to explain how this can be glued to provide a functor between, so to say, glued categories. But first, I want to just discuss this gluing procedure in general. Now, first of all, this word can refer to many different things. And the specific kind of gluing that I'm talking about here is not about looking at a cover, but rather about the situation where there's, say, a topological space. So this is an example. A topological space, an open subset y0, and its closed complement. And then our goal is to construct, so to learn to recover geometric objects on Y from their restrictions to this open and this closed. And when I say geometric objects, it could mean many things. So cover objects on Y from Y0 and Y1. So, for example, if we are just talking about functions, this would be quite easy. I mean, a function on Y is determined by its restriction to this set and its complement. But already, if we look at things like sheaves, then this becomes trickier. So how does knowing a sheaf on an open set and a closed set, what do we need? So it's already clear that you need some extra data to recover what's happening on Y. And similarly, the things I'm actually interested in are categories. And there the situation is similar. Again, you need some extra data for gluing to occur. So specifically, this will be applied. This procedure will be applied on will apply at least on both sides of the Langlands transform, and the corresponding categories. So you can say that the goal, the plan of the proof of the geometric Langlands conjecture is to construct a correspondence by gluing the two objects that already appear, the correspondence on degenerate and on non-degenerate Fourier coefficients. All right. So now let me start with this more or less abstract setup, and then we'll get back to the Langlands world later. So how do you glue sheaves? How do you glue categories? So let's I'll continue looking at these examples, and let me consider the category of sheaves. And let's say, I don't know, constructible sheaves of vector spaces. So just to be, I mean, I definitely don't mean quasi-coherent sheaves. I just mean something topological. So this is something sheaves of vector spaces. So, or maybe the derived category of such sheaves. So as it usually happens, I don't want to work with the abelian category. So then it's well known. So let me. Then it's well known how to relate sheaf on F to its restrictions to these two. So let me maybe, excuse me. So let this be y, y0, y1. So there's a open embedding and a closed embedding. And what we can do, we can send f to the space, to the sheaf of sections that are allowed to have singularities along y1. So that's this. And let me use, for no particular reason other than my desire to match it into the world of D modules later, let me call this the Schrick push forward, even though it's just restriction, doesn't really matter. So, I mean Schrick pullback. So there's this, and then the kernel consists of sections with support on y1. So this will be I upper Schrick f I lower star. And again, maybe let me use Schrick here again for no particular reason. Doesn't really matter. And this is actually an exact triangle. So continue. Now let me denote the two restrictions by f0 and f1. So this one is going to be f0, which is a sheaf on the open set. This one is going to be f1, which is a sheaf on the closed set. So now if we want to recover f, we can recover it as a cone of the maybe actually let me continue this sequence on the left. We can recover it as the cone of the previous map in this sequence. So specifically, so as the cone of the map from J lower star f0 shifted by 1 to I lower Schrick f1. And now up to this point, it didn't really matter whether I lived in the triangulated world or in the DG world. Here, I really want to move to the DG world, because in the DG world, this thing is actually functorial. So this really does recover f, not just up to a non-canonical isomorphism, but actually naturally. And so the summary is that we need, in order to glue a sheaf on Y, we need the following data. 2 sheaves on the open and the closed, 2 sheaves on the strata, and a map like this. So let me restate it. So equivalently, using the adjunction, so the following data are required to reconstruct a sheaf on all of Y. So I need required, I guess, gluing data. I guess that's the best way of putting it. So I need a sheaf on the open, sheaf on the closed, and somehow maybe I should call it an attaching map. So let me call it, which by adjunction can be rewritten as follows. So it is now a map. Let me write gamma f0 to F1, where gamma is the following functor from Sheaves on Y0 to Sheaves on Y1. So it's just, well, I just have to move the Schrick on the other side. So, well, I guess maybe here it would be really help to have star rather than Schrick. So it's you can either write it, you can write it in two equivalent ways. You can write it as I star j lower star, but then you need a shift, this shift -1. And it's a nice exercise to see that this is actually the same as I Schrick j lower Schrick. So somehow this well, I don't think, am I messing something up? I don't think there is. I think this is the fundamental fact. There's no codimension 1 anywhere. So because, let me tell you another way of what this functor is. You take the extension by star. So let's see. So you take a sheaf on the open set. You take its extension by star, and you take its extension by Schrick. There's a map between the two, and the cone of this map is supported on Y1. Now you can either hit this, if you hit this sequence with a star, it will, with star restriction, it will annihilate this, and you will see that cone is essentially the star restriction of this. If you hit it with a Schrick, it will annihilate this, and you will see that the cone is the Schrick restriction of this. Now this is true only up to a shift, because in one case I'm putting the cone on this side, and in one case I'm putting the cone on this side. So I think this is completely, this has nothing to do with codimension 1, this is just fact of life. Any other questions? So all right. And so this is the data that's needed to reconstruct a sheaf. Now let's upgrade this and think about it as our way of defining some category of gluing data corresponding to Y0 and Y1. So let me, so this is maybe the main abstract definition. Yeah, very simple one though. So definition. So suppose we have two DG categories. And suppose that they are connected by a functor from C0 to C1. So an exact functor, I guess. I'm going to define the glued category. The corresponding glued category, which I'll denote just some. I mean, here I'm thinking about DG cat. There is a version of this in the infinity setting, but I'm thinking of DG categories as realization. So this is. I'm not sure. I really want to work with strict. So maybe the G functor. And, yeah, but the exact the G functor. Well, I'm working, I mean, the infinity categories are essential when you try to work with things that are non-linear. Here I'm only working with linear objects, so I don't see what I win by passing to infinity categories. I mean, you can call them infinity categories if you want, like stable infinity categories. It's fine. But anyway, so we define this to be the category whose objects are triples like this. So there's an object in one category. Let me call them C0 and C1. So there's an object in one, object in the other, and a map and the map from one to the other. So I'll just write gamma C0 maps to C1. Of course, the interesting question is how, well, I just defined objects here. So if you want to define morphisms, it's a little bit more interesting because you're supposed to have a commutative diagram somehow naturally. And on the other hand, you also work in the DG category, so you don't want to just require that things commute explicitly. So let me, to remove this ambiguity, let me give a... Yeah, I mean, that's exactly what I wanted to say, that you can just define home. I think if I'm using DG world, I can write home rather than maps, right? So this is just, I'm just thinking of this as a complex. So home in this new category between two triples, I'll just write, yeah, that's okay. So can you see the primes? So this one with primes and one without the primes is
by a map, you mean a map is
H naught. Yes.
By difference.
Yeah, and an element in H naught. So this is going to be the cone of the following, or rather homotopy fiber, so shifted cone. I'll add a shift in a moment. So there are maps between C0 and C0 prime. Then there are maps between C1 and C1 prime. And these maps, both of those actually map into maps in C1 between, now let me make sure I get it right. So there's gamma of C0 and C1 prime. Yes, I believe this is fine. And we want the fiber of this map. In other words, up to the G stuff, I'm saying that I want the kernel of this, which is exactly some kind of relation. So I'm saying I need a map here, I need a map here, such that the two compositions which land here coincide. So this is a very explicit example, and now I can use this a very explicit definition. Now I can use this definition to finish this example by saying that this claim here is that the category of sheaves on Y is the gluing of the category of sheaves on Y0 and the category of sheaves on Y1 via this functor. I guess I was using this notation. Right? Does it make sense? Are there any questions?
What you give is a cycle or an element of L0?
What I give, yeah, it should be a cycle. Sorry, did I say an element of?
Yes.
Okay. Sorry. So it should be a cycle. Otherwise, yeah, otherwise you will not be, so.
It's not entirely clear which Cs are small and which are big in the middle.
Okay. Well, all the sub-indexes are big, but yes. I think I'll stop using this notation now. So probably it's too late to fix this one. But thank you. That's what I'm going to do in a moment. So this is the question is whether you like formulas or whether you, took the warning to the heart and never want to write a formula again in your life. So this is a formula. There is also a more somehow categorical definition in terms of universal properties. Specifically, this is what is called a lax limit. So equivalently, and I'll just call this C, but there will be no more objects. Just so now this C is the lax limit of the short diagram gamma from C0 to C1, and by definition, having a lax limit means that we have that there is a functor from C to C0, a functor from C to C1. There's also part of the data, part of the input data is this functor from C0 to C1. However, this diagram is not supposed to commute. There is only supposed to be an arrow in one direction. So there is a functorial morphism between this composition and this functor. And the whole thing should be universal. So C together with these two functors in such functorial morphism is universal. What? No, it's a morphism. That's why it's a lax limit. So it's a morphism, but it's not an isomorphism of functors. So there is a universal diagram where this arrow is a functorial morphism. And the key point is not that it's a functorial morphism, but that it's not required to be an isomorphism. So it's important that the part iso is missing here. Any other questions? All right. So let me also mention that, in fact, you can start from this diagram. But once you have this structure, there's a lot more that can be said. In fact, so a remark is that the three categories are actually connected by 6 functors, just like in the general case of, just like in the case of this, in the topological example. So in this situation, that is, if C is obtained as the gluing or the lax limit, whichever terminology you prefer, there are 6 functors. So such a diagram is called a Recalman. And conversely, if we have such a nice diagram, it establishes C as a gluing of C0 and C1. Somehow the advantage, again, the advantage of working in the DG world is that all the data is encoded in this one. So the whole thing is completely reconstructible from 2 categories and the gluing functor between them.
This to map is a cycle also between functors. The map,
well, it's a functorial. Well, if you are willing to look at lax limits, then then presumably you are very comfortable with categorical with infinity categories. So okay, no, but yes, it's supposed to be universal in the here when you need to actually understand what it means to be universal. So
it's a categorical cone.
I don't see why it's a cone. A cone is like the same thing when you had a zero when you have two maps. Cone is more like an equalizer.
Cone of a function.
No, but I think cone is generally an equalizer, right? You are setting some things to zero. Like, for example, if this is an isomorphism, the answer, you don't get 0. You don't get 0, you don't get 0. So it's always a larger, it's really more like an extension of C0 by C1, and this gamma is the extension class. So the size of this category is, roughly speaking, this.
So again, so Lax limit is a term from the theory of infinite categories.
Sorry, what?
Lax limit is a term from the theory of
Infinity categories, but it's also, yes, you don't really need infinity here, just to listen. Yes.
Like Tablata and Drinfeld, they work out like a modeled category of DG categories. This looks like the homotopy limit they would have constructed.
Well, I mean, I'm not claiming that this is anything new, but I don't think it's the homotopy limit.
That's not it.
Right, the homotopy limit is just a right version of the strict limit, right? And this is the fact that it's lax is, I mean, this is different. Like, there is no point taking strict limit of a map from C0 to C1. It's just going to be C1, C0. Okay, I got it right on the second try. So, and by the way, if you really want to play with this, you should notice that this diagram is very symmetric. So you can also cook up a bunch of triangles with some arrows or pointing in different directions. So the precise statement is that you can also realize C as an op-lax limit, lax co-limit, op-lax co-limit. I think I ran out of possibilities. So anyway. All right. Now, this is the end of somehow formal part. There is, in principle, more to be said. If you, another thing you can try doing is to generalize what happens when you have a stratification with more than two terms, which would correspond to lax limits along some more complicated directed set, in fact. And it's not that hard to figure out, but I'll leave it to you.
Maybe see an example, like something simple.
But, well, the topological example is really the motivating example.
No,
Well, but I mean, what's the difference? It's there are, I mean, you can call it, so somehow the point is that you look at.
No, I mean, say you have a DG algebra A, DG algebra B, and a factor from category of DG models.
So it doesn't work for quasi-coherent sheaves so nicely because you usually, well, I mean, again, in what situations do you have this kind of a diagram? So sometimes it's. Yeah, but I mean, so you are asking for some kind of DG examples. I'm saying that there is a classical, somehow triangulated world, and there are, you know, there are many, well, not many, there are some examples where these things appear. So wherever these things appear in triangulated world, you would expect this lax limit that in the G world it can be written as a lax limit. Sure. Well, I mean, you have to. The question is whether if you have a Kalman in the G world, it automatically produces this gluing, and I want to say yes, but I'm not sure what is the definition. I mean, I want to say that if you have a quotient of a category, subcategory, and then there's localization, and it turns out that accidentally one of the functors has an adjoint on the other side, then this situation works. So Yeah, I think I'm justified in saying this. So yes, this is a statement. All right, let's move on. And so, all right, now we still have two sides of the geometric Langlands to go over. Let me actually try to put somehow the main diagram on the board. So there are, well, two sides, the geometric Langlands, the geometric side and the Galois side, metamorphic side and the Galois side. On the geometric side, the category of interest is this extended Whittaker. And it's very natural to expect that, well, let me actually, I'm not sure how to arrange these things on the board. So there is a, let me put them. So there is the usual non-extended Whittaker category, and then there's the category of principal series. Sam, what was your notation? I'm sorry, I don't remember. So, aha. Okay. All right. So, and it's reasonable to expect, and in fact it is true, that this category is obtained by gluing from these two. So in other words, that there is in fact a gluing functor. So then we can construct the glued category. Well, so it's an example of this situation. Now I'm out of room. And now the two categories will be equivalent. So on the Galois side, well, I'm saying that I'm staying on the geometric side, that the extended Whittaker category is the gluing of these two categories. So it's not a very deep statement. But there is something to prove, and I'll come to it in a moment.
Don't you need the other parabolics?
Oh, sorry. Yes, I apologize. Yes. So for now, I think for the rest of my talk, I will assume that my group is GL2. This is not really 100% necessary, but since I only covered the basics in this case, I will only work. So well, let me assume GL2, so then there's no question. Okay, sorry for this.
There are no other parabolics.
That's right. So indeed, I mean, the main property of GL2 that makes it life so easy is that there are only two parabolics. So there's G and there's B.
But in some talk we didn't even, we also just discussed GL2, right?
Yes.
When I talked about the extended Whittaker model, I assumed for simplicity it was GL2, but the theorem about the closed stratum, it didn't have to do it. It was for a general reductive group with the principle.
That you just compared GP to something.
Yeah. That is fine.
OK. Fortunately, my notes just ran out of electricity. So now on the right-hand side, we know counterparts of these two categories. There's the category quasi-coherent. Somehow, no, there's absolutely no way they can fit here. So let me move the Galois side here. So on the Galois side, we have the following counterparts of this. So there's the category of quasi-coherent sheaves on log cis. G check technically, although since I'm assuming G is GL2, this is a little silly. And this is one of those categories. And the other category is the category of quasi-coherent sheaves on log cis. And let me use Sam's convention and just shorten it to LS to save time, of the Borel subgroup. But these quasi-coherent sheaves are supposed to have connections along the projection downstairs. And again, I will discuss the two sides separately in a moment. For now, I just want to get the picture on the board. And it's not hard to see that there is a natural functor between the two categories. And we will just declare our glued spectral version of the extended Whittaker category to be the gluing of these two. So I will.
So you want say in a quasi-core of just log cis G check. This is going to be the same as Whittaker?
I didn't say it's going to be the same. In fact, the relation between the two boards is that the right board fully faithfully embeds into the left board. So there's a fully faithful. So the way I'm setting it up, I don't get an equivalence. Rather, I get a fully faithful map from right to left.
We did have a local description. I mean, we did have a description of Whittaker.
Yes, which had the rep G check, and I would rather work. This is what Sam was talking about in his talk. So that you can, in case of GL2, you can somehow, using the functors between rep G check and rep G check run rather, and this, you can somehow replace it. But in general, I think it's. I think it's, at least at this point, I find it easier to work with this category and just sacrifice the essential surjectivity of this functor. Just leave it as fully faithful functor.
Do you expect in principle to have some uniform description of the glued category? Like, I mean, in your definition, it will be artificial.
You mean something natural rather than gluing of these two? I don't know. It would be nice. I don't know if it's too optimistic to expect it. So at this stage, we don't have something. So anyway, so there's a glued category of these two things. So again, this kind of diagram. And this is just, I guess, by definition, I think a different notation was used in Dennis's, or maybe, oh no, Sam, you had it something else, right? So
Gino, what is happening? So now this quasi-coherent, maybe Ind-Coherent was some important condition.
But this is exactly the point. The key statement is that the category, again, we're getting a little bit ahead of ourselves, but maybe, I don't know. If everything's on the board is clear, then, so the key point is that on the geometric side, there was a theorem from Darius' talk. So maybe I should put names on this. But anyway, so there was a theorem from Darius' talk that said that D modules on band G actually embed.
This was a conjecture.
Well, if G is GL2, it's not a conjecture. But yes, if G is GLN, this is an actual theorem. This is a theorem, almost a theorem. And if G is, for other G's, it's wide open. Not a theorem. OK, so this is the picture on the geometric side. And the claim, somehow the meaningful part of my talk, well, there are two meaningful parts of my talk. First of all, it's an explanation that we can match, somehow match the bottom lines on these two boards. So the individual categories already appeared. It was discussed how this category embeds into Whittaker and how this category embeds into the degenerate Whittaker. So my point is to say that in order to construct the gluing, all you need to know is that this embeddings are compatible with the gluing functor. So if these embeddings are compatible with the gluing functor, then we get an corresponding embedding between the glued categories. This is one thing, and this is one somehow non-formal part of my talk. And the second non-formal part of my talk is that, in fact, there is an embedding from the category, from the right-hand side of the, from the Galois side of the geometric Langlands correspondence, namely from this category Ind-Co global nilpotent cone on the stack of local systems, into this category. Now, this is a theorem. It's not conditional on anything. So it's, again, as I'm setting, the way I wrote it here, it's only set up for GL2 because I only consider two parabolics on the board. But it's a theorem for arbitrary reductive G. And despite the fact that, like you say, there's no Ind-Co, when I say embedding, I mean fully faithful functor. So all hook arrows are supposed to be fully faithful functors.
Oh, we need another description, not as a gluing, but explicit description.
Of what?
Of this critical theorem, or just as a gluing description.
For what? For this theorem?
Yes.
No, this theorem relies purely on this glued description. So it's, I mean, I really don't know how to describe this category in some more understandable terms.
How far is it from being an equivalence?
It is pretty far from being an equivalence. For example, I mean, the point is that this is somehow over-communicating. That if you, I didn't actually say what this functor is, but this functor is a kind of pullback. No, it's pullback. This is G, this is B. So there's a map in one direction. And so the functor is a pullback. And so in particular, if we have a quasi-coherent sheaf on log Cs, we're going to remember this sheaf, and we're going to remember its pullback to log Cs B. So you don't really need both pieces of the data to reconstruct the quasi-coherent sheaf. So this is, so it's not really an equivalence in any meaningful sense. But I mean, neither is this map for that matter. So this is theorem, maybe main theorem. Let me.
Yeah, I think that after discussion with some, you should remind what the gluing functor between Whittaker and the degenerate Whittaker is.
I should do a lot of things, but I also feel that I must answer the questions. Am I? So.
I mean, what I said now is a question. what is the functor?
Okay. Now let me. Now in the remaining 15 minutes, I want to discuss these two sides separately. So let me first say what goes on the geometric side. Now, the picture on the geometric side is a version modulo all the infinities, is a version of the topological story that I started with. So recall, I don't really need details at this point, that these various Whittaker categories were defined as full subcategories of certain categories of D modules. So specifically, there was this extended Whittaker category sits inside. Let me just denote it by Q extended. This will be consistent with at least some nodes. So this sits fully faithfully inside the category of d modules on some and d modules on some space. The details are not important right now. So this full faithfulness is given by some equivariance conditions. And again, the details are not important in the moment. And this space has an open subset given by the condition that something is not 0. So this will be the map J. And it has an open something, closed something. Running out of letters. I thought it was something like GB, but again, I'm sure that I'm very far from your notation by now. So this is closed, given by the condition that certain character is 0. No, WGB is the category of sheaves here with the condition, with the equivariance condition. So
go with NGB rats.
I thought we decided not to talk about rats. So, but yes, I mean,
about cats.
Yes. So anyway, this is something like ban. I think Dennis wrote it as ban G B gen. Right, and then we impose the equivariance condition with respect to something like n over dels. Anyway, but again, like I said, the details are not important. All that's important is that there are open and closed embeddings, and that these categories are the categories of d modules supported on open stratum, on the closed stratum, together with this equivariance. So I guess I'll just write the corresponding categories. And then this WGB. So they're just cut out inside d modules. So this equivariant d modules again. The details, in some sense, are not that important. OK, and so therefore, I know what this glue-in functor is supposed to be. Let me now move this. Therefore, by the topological example that the glue-in is simply J upper shake. This is J. This is not a hat, just I lower shake.
J lower shriek, I upper shriek.
It's OK. I mean, there's only one way in which it can be written that it makes sense. So thank you. All right. So we're done. Right? I'm wondering if I can get away with this. So
Making a specific claim that this J lower shriek is defined.
right. I mean, there is a slight problem here, namely that in this in the topological discussion, I needed all of the 6 functors to be defined. Well, in fact, I only need, it's enough to know that one of the unusual functors is defined. So I needed to have a situation where there's some kind of extension by 0. And for d modules, this generally speaking fails. So there is a statement built into this. And this statement is necessary if we want to apply the glue-in machinery. So namely, for this glue-in functor to exist, this J lower shriek must be well defined. So this depends on J lower shake being defined. Now, where does it? So, in principle, J lower shake, in an ideal world, it will be defined on. So you can try applying it to D modules on Q, but then there's no reason to expect this to work if D modules are not holonomic. Generally speaking, that this functor just won't work. So the claim is really that this that it is defined on the Whittaker category. So being defined on the Whittaker category, which is a full subcategory in the category of D modules. Yes, it's connected with holonomic. In fact, that's not a hard statement. So let me proof of this claim. So this is. So let me not answer this. So, but roughly speaking, the answer, the idea, and the important step in this is that we have a lot of symmetries of the situation. We have this entire Hecke algebra, so to say, or rather the category of. So everything is equivariant under the category rep G check ran under this action. And so this category, as was explained, is actually cyclic under this action. So it's generated by a single object. Because of this, it's enough to verify that this functor is defined on this single object. Need to check that J shake is defined on the generator of this category. And this generator is holonomic in an appropriately defined sense. Okay. So this is the end of the. So the generator is this first. Well, yeah. Informally, I want to call it the first Fourier coefficient, but this is this J mean that was discussed. So just to remind you, there was an equivalence between, or almost an equivalence between the Whittaker category and the category of representations. And the way it was set up is you act on a particular object in the Whittaker category. So this is the generator. And the claim is that this generator is sufficiently nice that you can check this extension somehow from geometric statements. OK. And so after this part of the story becomes no longer conjectural. It's an actual statement. So somehow one sad part of the story is that this, and in a certain sense, it's not enough. So this functor, the gluing functor, if we want to match it to the spectral side of the story, we need to know explicitly what it is. So it's not enough to just say that it's defined. We actually need to compute it. Fortunately, we only need to compute it essentially on one object, on this generator. So this is like computing constant series, a constant term of some kind of Poincaré series here. OK, now let me cover the statement and uncover the Galois side. Now, what happens on the Galois side? Let me set up this diagram. So on the Galois side, the following, there are only two spaces involved. This is the good news. There's the space of local systems of a B check and the space of local systems of a G check. And there's an arrow relating the two, which might be, I'll denote it by P sub spec to remind us that we are on the spectral side of the Galois, on the spectral side of the Langlands correspondence. So this is the arrow, and then we are interested in the following categories. Well, for now, I'm only interested in this bottom row. So there's the category of quasi-coherent sheaves on local systems, and there's a category of quasi-coherent sheaves on on somehow, I guess, flags in local systems with flags. But these sheaves are supposed to be to have a connection along the fibers of this map. I guess this is not the notation used. So should put ls G check. All right. And so now, in order to set up the gluing, I need a functor between these two categories. And the functor will be simply the pullback. I'm going to call this pullback P upper shake. So because I'm thinking of, so in Sam's talk it was explained that the category upstairs maybe, well, you can think of it as in different ways. You can think of, say, quasi-coherent sheaves with the connection along the fibers, but somehow a more, well, you might have noticed that we like Ind-Coherent sheaves. So we think of this as Ind-Coherent sheaves with a connection such that forgetting the connection makes this sheaf quasi-coherent, not just Ind-Coherent. So again, maybe I shouldn't go into this. Another way of thinking about it is that I'm just thinking of this as a quasi-coherent D module, but a quasi-coherent right D module somehow. And then this pullback will be as expected. OK, so anyway, there is this functor, and an important technical point is to make sure that the two gluings match. So need to check that the two gluings matched, and this is not completely done at this point, done to the extent to which it can be done. The reason it's not completely done is because we need to match the corresponding categories, and this, as was explained in Sam's talk, is not, I mean, it seems plausible. There are ways to approach it, but it's not a theorem yet. I mean, even for GL2, the match between this and this is not a theorem. It's almost an almost theorem. So the two gluings are matched. I know. I was trying to decide whether I should leave match or whether I should put unmatched, and I decided to use kind of newspaper style. But thank you. OK, so this now let's believe this. Let's believe that the two gluings match. And then
this is something no.
hello. OK. To some extent, to the extent to which the two sides match. So and so let me now state the main theorem the main theorem involves embedding this category into the glued category. And so let me actually, now I publish.
Another one of this big category, which was the models of Q extended on the spectral side.
Sorry? Oh, you mean the big meaning without equivariance condition?
Maybe.
No, but I mean, it's a weird category from a certain point.
You can try to include both.
No, but the point is that they won't glue, because the gluing geometric gluing functor depends on the equivariance condition. It's not necessarily defined on D modules on the entire Q. So I don't think it's a reasonable thing to do to drop this equivariance condition. OK, so let me set up, let me maybe prove or state at least the last this main theorem more precisely. So I need to tell you how the Ind-Coherent derived category embeds into the gluing, which happens in the following way. So let me look. So this will be the quasi-core side. This will be the Ind-core side. So that's the category of Ind-Coherent sheaves on local systems of G check, from which there is a forgetful functor. Not forgetful functor. There's a colocalization into the category of quasi-coherent sheaves. Now, given an Ind-Coherent sheaf on G, I can lift it under this map, pull it back, and get an Ind-Coherent sheaf on B check. And because I'm pulling back along this map, so the functor is the pull back, P spec shake. Because I'm pulling back, this will have a connection along the fibers. Now I can also do the same thing, and I already did the same thing for quasi-coherent sheaves. I'm almost there. So again, this functor going up is the same, essentially the same pullback, but now in the quasi-coherent world. And I can close this square by using psi upstairs. So I have this, always have this somehow colocalization functor, this that loses some information by passing from Ind-Coherent sheaves to quasi-coherent sheaves. Basically, if you think in terms of singular support, this is like taking something whose singular support was large and taking sections with support and singular support in the zero section. So you erase everything whose singular support is not zero. OK, so we have this diagram. Now, the problem is that this diagram does not commute. It's as written, it's p shake. That's why I said. The point is that I'm using psi to relate the two categories. Or if you like, you can use psi in the other way. And psi does not involve twist by an omega. If I use epsilon instead, or epsilon, whatever, then I would have star. So it includes twist tensoring by. So
why is it defined?
Let me consider this thing by definition to be the full subcategory here of things with support supported in the zero section. So this is somehow the easiest way to say things. All right. And so we now have this kind of diagram. And my point is that, in fact, it does not quite commute. Instead, but it sort of lacks commutes. There's an morphism in one direction. And the reason why it does not commute is the following. You can have something whose singular support is away from the 0 section. Then it would be somehow erased by this functor. However, it's possible that when you lift it up to B, the singular support actually partially will end up along the 0 section. This is functoriality property. So when you look at the functoriality of the singular support, you need to know how the shifted cotangent spaces map to each other. And it could happen that this map sends a non-zero vector to a 0 vector. So for this reason, you only get lax commutativity. And it is this reason why, when you do this, you might actually, you see more than just quasi-coherent sheaves downstairs. You actually catch some Ind-Coherent sheaves.
I think your arrow should point in the other direction.
It's possible. And like I said, my notes are not here at the moment. And are you sure? I think the way I set it up.
It looks to me like you go up, and then the formula is psi of p upper shriek.
OK, let's leave this at the moment. So let's just leave it as is for now. I'm not sure. Anyway, so my point is that in this way we get exactly an equivalence between. So main theorem is that it's exactly the nilpotence condition that gets caught in this way. So if you add support, if you add the nilpotence support condition here, so the resultant functor. So from this diagram, we get a functor from this, which is on the spectral side of the geometric Langlands transform to the glued category, which was also denoted. So it's this somehow extended spectral version of the Whittaker category. You get the functor from the full Ind-Coh, but it's only an embedding on the nilpotent, on the things with nilpotent support. In fact, everything else gets erased, so it factors through colocalization. So it's Whittaker extended spec, and the meaningful. So the resultant functor, I didn't finish the sentence, is fully faithful on the category with support, on int or nilp of the same thing. So,
is it true that this is the biggest thing on which it is fully faithful?
Yes.
This way you could guess that Ind-Coherent is the good guy?
Yes. But this is somehow dual to one of the ways to guess it. This was actually the way we guessed it, or Dennis guessed it. Yes. I mean, it's factors through colocalization onto this. All right, and so to summarize, if you believe all this, now I claim that now the two sides of the geometric Langlands conjecture, this category and this category, actually embed into the same global Whittaker category on the board. So somehow they both embed into their own versions of Whittaker categories, and the Whittaker category, the spectral Whittaker category embeds into this Whittaker category. So to summarize, both sides of the correspondence embed into this. And when I say embed, I mean fully faithfully. All right, so this is all I have to say. Are there any more questions?
So what is this second way to understand that Ind-Coherent is the right?
Well, you can, instead of here, I was lifting things up. Instead, you can somehow look at the adjoint picture and try pushing things down and see what's generated in the category Ind-Core. So you can look at the category Ind-Core, put there inside sits quasi-core, but then there are also some visitors that come from this different, well, in this case, only from this barrel. So you can try putting them there and then see what they generate, and they will generate exactly this.
I was going to ask more or less the same question. So for any group, you can also do this, right? I mean, for this on the Galois side,
yes.
This embedding is fine, right?
I thought I said that. Yes, it is.
You said that, but
Yes, this theorem.
I keep in my head everything you said. So.
Can't blame you for that. Maybe I'm lucky. That, you know. Anyway, but yes, this theorem is actually true. The correct version of this theorem is true for any reductive group. Okay. Other questions? All right. If there are no questions, then we will break until 5. And I don't think so. I think we have Q&A after, after we're all done. You want to have Q&A?
I want to maybe to reiterate some points for like 5 minutes.
I mean, it probably would be a nice idea.
You can ask both ask the questions.
No, I can ask questions to Dennis.
Let's have 15 minutes break.
Yeah, let's have 15 minutes break and then.